Good morning, good afternoon, good evening, everyone. Thank you very much for attending the October installment of our San Diego Big Chapter IEEE webinar. Hope you and your family are staying well as we're hopefully emerging out of this pandemic. With the use of webinars, we have the opportunity to broadcast the event to a broader audience. So today, we are absolutely pleased and honored to have Dr. Chidi Chidambaram from Qualcomm. He's the Vice President of the Process Technology and Foundry Engineering team, talking about semiconductor challenges in going from 5G to 6G. Obviously something of great interest to many of us, especially in the San Diego corridor. So just a brief couple of words about Chidi. He's the, obviously, as I mentioned earlier, he's the VP of Process Technology. He has done a lot of pioneering work in strain engineering, SOI transistor development, and so forth. Chidi worked at Texas Instruments prior to this, and I believe you received your PhD from Colorado School of Mines, correct?
Correct.
Yeah, fantastic school. Anyways, he's an IEEE Fellow. Contributed obviously tremendously to the publication community at IEEE, we're absolutely honored to have you here. Anyways, take it away. Thank you.
Thank you, Alvin. Good morning, everybody, or good evening, wherever you are. So Alvin asked me to talk to you guys a little bit about the semiconductor industry and the process technology challenges we are facing as we are trying to go to later generations of 5G and eventually 6G. That's kind of the focus of my talk. At Qualcomm, we believe we are really at the verge of a fourth industrial revolution, and the combination of 5G, IoT, and AI is really behind this, right? So in this picture, I want you to kind of focus on a few words like immediacy, autonomy, and security that will come back to in time. So if you look at human civilization, we were kind of living as isolated cities and countries for a long time, and then industrial revolution came along in the 1800s, and world became a small place, right? And eventually a lot of the transportations kind of created the second revolution, and the computer and the cell phones are the start of the third. But right now, with our ability to connect everything to everything, we're going to see a total change in how the technology is impacting human civilization, which is just at Qualcomm. And I think Cristiano says this a lot, that we are right at the verge of fourth industrial revolution. If you look at 1G, 2G, and 3G, and even 4G, it was primarily a people-to-people communication vehicle, right? The cell phones enabled a lot of things. People started able to reach anyone when they are on the road, and the data rates and latency improvements kind of took us all the way to 4G, where smartphones became a very common thing. At 5G, there is a lot more of people to things type of connections that are possible. Like today, I control my thermostat at home using my cell phone, and as a person using my phone, I'm able to control a lot of things at home, kind of, right? So the connection density and the number of connections that you need exponentially goes up as we start moving from people to people to people to things. But really, the later generations of 5G and 6G, eventually, what you're going to see is a thing-to-thing connection. Now, this is going to increase an order of magnitude in the connection rates, and for a lot of these things to be working to provide the user experience that is demanded, you're going to have to pretty much have a guarantee on the latency and security and things like that. So we'll see a little bit of that as we go along the talk. If you look at the semiconductor industry in a historic terms, right, I would say kind of 40 years ago, it was primarily a compute-driven, IDM-based industry. They were kind of just coming out of discrete components and vacuum tubes and transistors and diodes of that nature, trying to build VLSI circuits to start to do logic computing in general, and really the servers and the start of the PC revolution was the 1980s, right? So these were all like 100K units and you know, integrated device manufacturers, IDMs were the norm. And the kind of innovation they had to do going from vacuum tubes to VLSI was a strategy of design for test, right? So we started doing some testability, and because you now have lots and lots of transistors on the same chip, you had to test which one is failing, and you have to have a scheme of how do you do it. 20 years later, mobile phones really changed the equation. You know, we now start shipping in the millions of units as opposed to 100,000s of units, and handheld low power logic became the driver. So a lot of power-based engineering becomes very important. Power gating and low leakage transistors, things like that. And that's around the time where fablesses were becoming popular, as you know, companies in Asia like TSMC and UMC were starting the fabless ecosystem, and it led to the creation of large fabless companies like Qualcomm, NVIDIA, and all these guys who now don't need to own the fab, but could do the design ourselves. And then, you know, now you know, as you start getting into more and more transistors, you had to plan for a design for manufacturability. So now you got restricted design rules, and you're not allowed to do a lot of things that you would like to do just so that it can yield. 20 years right around now, we are at what I would call the 5G IoT AI era, and in this space, it's not just the cell phones, but lots of connected devices at your home, at your car, at your industry. Everywhere is kind of taking off. And now, in order to do this, you know, we used to have a few radios on you know, 40 years ago, there were only radios in your transistors and TVs. But then with a mobile phone, you got radios with all your handsets. Now you're talking about radios in every single equipment that you own, right? So now this is a explosion of a lot of the RF components, and then it enables a lot more AI implementation that drives a lot of data rate increase, and then there is a lot of CMOS for low power logic processing anyway. And now we are talking about billions and billions of units, and to make these type of really low cost, long lasting IoT, AI, 5G devices, you need a total system engineering. So you'll see that's one of the key messages out of this talk, where, you know, we have to kind of bring a language that the entire system can talk with each other. And with this, I would like to propose the term DFD, like TFT, DFM. We are now on DFT, which is really designed for durability. So semiconductor industry is generally not used to building stuff that lasts for 5-10 years or more, right? We were kind of in a very fast replacement cycles of laptops and PCs and cell phones. But now, you know, we're talking about sticking these things into cars and refrigerators and things like that. So these are pretty long-lasting products. So we have to change the way we do our manufacture and design. They really have to get into a space where they are going to last for 10, 20 years type of time frames. Let's take a look at the intersection and kind of visualize how the later generations of 5G and eventually 6G were going to play a role, right? So here, you know, we are looking at an ecosystem where we are now able to enable a lot of edge AI, which will go into your cars, and they're called the ADAS system, where they are driver assistance systems, which they have LiDAR or optical cameras that are looking at the road ahead of you and telling you if there are any obstructions along the way. You know, it would have enough intelligence to distinguish whether the thing that's flying in or moving in is that a brown bag or a boulder that can really break your car, right? So and then there is going to be a lot of connections just at this intersection. So the signal site, the unit that we install on the signal light is called the roadside units, or RSUs. And then there are pedestrians walking with their cell phones and watches, or even VR glasses, whatever they may have. So the protocol that is being adopted by IEEE to make all these things work is called CV2X, which is connecting vehicle to anything, X for anything. Used to be vehicle to vehicle, but then they started calling it vehicle to everything. And these things have a lot of guarantee on how quickly they will register, right? So because if the car needs to brake just reacting to the pedestrian stepping on the street, the guarantee of this connection and the latency with which the reaction should happen is very essential, right? So it's as a part of the 3GPP, 5G protocols that have guarantees on a lot of these things. And so now when this entire system is enabled, and if the latency improves from earlier 5G into later 5G is down into sub 3 microsecond type time frame, you can visualize a situation where the roadside unit is simply the administrator of the intersection, and it's no longer going to flash a green or red on you. It's just going to talk to your car and accelerate your car at the right speed, so all the cars can go through the intersection without stopping. I think these are eventual applications that are really possible once all the AI and the CV2X and the 5G and the latency guarantees are all established. So it's a pretty exciting future, but to get there, we need a lot of things to happen. So we'll review the outline. I'm going to talk about, as we talk about these visions to come true, what are the needs, right? What are things we need in the 5G and the 6G system integration? And look at the industry today, what are the technologies that are available in all areas, like digital, in the PA, LNA, switch and filters, transceivers. What are the existing technology challenges? And then we'll look at what are the things that are going to come up in the next few years, and then how we are going to put it all together as a system and RF integration to get the final solutions. That's kind of the brief outline of my talk with 4 key sections. So let's just jump into what the 5G, 6G are. So if you break down really, what's different between 4G versus 5 and 6G, it's really 3 things, right? We talked about the latency. I think I gave you a very good example of how traffic manager on a RSU unit can just take over if the latency is guaranteed. And then we talked about the bandwidth, right? You need very high data rates because you're now doing a lot of AI workloads, right? So the AI is all about tons and tons of data, and your AI engine is going to take the data and interpret whether it's a brown bag or a boulder. But to do that, it needs to capture from multiple LiDAR sources and camera sources and process all that information to get the inference so you can have the reaction. And also we talked about as thing-to-thing connections, right? As opposed to people-to-things or people-to-people, each of them kind of takes another exponent in the number of connections that are needed. So if you really want to think of an industrial shop floor where a car is getting assembled, there will be, at least hundreds of robots, and each of them will talk to each other to know what's coming down the line and what exactly was put in that particular car and what should the next robot pick up and place and weld or do whatever, right? So all these things have to be connected. So the number of connections are massive. So all these 3 things are really the key that's going to drive us into the later 5G and 6G generations. To do this in a practical, right? Now we get into the reality. Your air outside has to have all the signals you need to make this happen, right? So let's take just a cell phone as an example. I could take my cell phone, go from San Diego, fly into San Francisco and go to Japan. And each of these regions have very different base stations and band structures and available. So your chipsets that you're going to build have to be able to understand and deal with all of this. So that's kind of what this picture is trying to show. So here, this is the entire electromagnetic spectrum, right? So if you look at the entire cell phone of last 20 years, we were just living in this left edge of this entire spectrum, right? That's all we were. All of 2G, 3G, 2.5G, 4G are all just this. Now with the sub-6, as a part of the early 5G, we kind of expanded into this spectrum. And even here, right, there will be, Sony in Japan is using this, and TDK is using this, SK Telecom in Korea is here, China Mobile is here. So there's all kinds of combinations of various bands that are used in the world. And this chart kind of shows you how a cell phone needs to pool whatever resources it has together to provide you the bandwidth, best bandwidth possible, right? So these are called what are known as carrier aggregations. So it kind of detects what are the channels available, frequencies available in a given region. It finds out, I have a 3.9 gigahertz band and an 800 megahertz band, and I need to aggregate the two to get you something like 5 Mbps, right? So that's kind of like a line like this that's kind of aggregating together to get you these combinations. So think about how exactly is going to happen in the chipset, right? I have to have, for each carrier aggregation, I got to have each channel. So my entire scheme will have to bring the two in, and then the digital signal has to be merged, and then you are able to decode the two together to get the final data output. So that's why you're going to see, tons and tons of chips. To make all these combinations work, you need lots of chips. So it's good for the semiconductor industry. The volumes are going up and the number of RF components are going up. And as we go to millimeter wave, it's even more complex. I'll talk about that a little bit more in the later slide. So this is a little bit more detail of how Qualcomm implements the sub-6 and the 5G, right? The modem is kind of the digital end of it. It's sitting in this kind of center point, and millimeter wave and the sub-6 and LTE are the two different arms, right? Each of them have their own kind of transceiver front-end strategies and different antennas, and we'll kind of look at this in a little bit more detail later. But if you look inside, you're going to find practically every single technology that the semiconductor industry has to offer is a part of this portfolio, right? The latest node, like a 3 nanometer CMOS, is really where the digital modem and multimedias are going to be. And then each of them need a power management that's in a very old CMOS technology, like almost 25 years old CMOS technology. And then, you have the transceivers that are built on the first generations of FinFET, and the power amplifiers on the phone are built on gallium arsenide, and a lot of the traffic is regulated and sent into these channels and bandpassed using these acoustic and other filters that I'll talk a little bit about. So pretty much, if you want to see what the challenges of 5G, 6G are, you're going to see the entire gamut of all the things that are offered in the semiconductor industry. So if you double click on the previous chart a little bit more and look a little more detail, right? So now we have the center modem here. Right next to the modem sits the up-down converters. These are the RF transceivers. And then you have multiple routes, right? So these are generally called the RF front end, radio frequency front end. So on the transmit side, you have the power amplifier, and then it kind of regulates that and sends it to the antenna using a bunch of switches and tuners. And then on the receive side, we usually split them into multiple channels. There is a mid-band, high-band LNA and a filter, and a low-band LNA. These are all built as modules, and in the phone you can actually see these integrated as a modem and a couple of antenna modules, and there will be other diversity modules, PAMID modules, etc. Okay, so let's talk about the requirements now. I would say we can kind of look at them as three general groups, right? So the digital modem, which is primarily a digital, right? And on the receive side, you're kind of taking things out of air, really weak signals at minus 130 dB or so. And the first thing that comes after the antenna is an LNA. LNA stands for the low noise amplifier. And this basically has to take a really weak signal and amplify it without adding a lot of noise. So here the noise is the major challenge. And then you go to the up-down converter, and then it takes the radio frequency down to something a digital chip can handle. That's the transceiver. And these are usually built in, like I told you, first generation fins. And here, some noise is important because you're still dealing with weak signal. And high self gain is a pretty important aspect of this amplifier region. Then you go into the ADC, so you take the analog to digital conversions. Here, the resolution of the ADC plays a big role. You can have cheap 8 bits or go all the way to 22-bit ADCs, where you can get a very high resolution of the analog to digital conversion. So depending on your quality and the number of OFDMA and QAMs that you have to pick these things appropriately. And once you convert into the digital, you do all the OFDMA processing and extracting the data, and managing that is done through the digital signal processor and the modem. And on the transmit side, right, you now take these digital signals and convert them into analog, up convert to radio frequency, and pump a lot of voltage into the signal using a power amplifier, and send it out with pretty high output power, right? Like almost 20-30 dB outs kind of numbers. So that's kind of the entire sequence. And on the transmit side, you do have the PA, which needs to operate at a pretty high voltage, and there are some unique requirements that drive complicated 3.5s and things that are better suited for this. We'll talk about that a little bit more detail. And in all this, switches and filters are of course needed to traffic regulate the signals, right? Okay, not moving. Okay. So let's get into even more detail of what exactly does it mean to go from 1G, 2G, 3G to 4G, and 5G, sub-6 and beyond, right? One of the key components is what's called a broadband. So if you look at the lower protocols like 2G, 3G, we use a very good narrow band, right? So these are pretty 80 megahertz or so windows that are easily manageable with the entire amplification system and the filtering system. But once you go to sub 6 and 3 to 10 gigahertz, the bandwidth has got to be much bigger, right? So it's what's known as a broadband, and now you have to have amplifier design that handles the ability to manage the broadband. In a narrow band, we typically used to build the chip separately, and then we build a matching circuit where you can put an add-on RLC to get the Smith chart-based impedance matching. But with broadband, you really don't have that luxury, and you really need to have the matching as a part of your design itself, right? So this is, you see this theme coming again and again, where everything has to get planned into the system directly. Otherwise, you won't have the opportunity to get the 50 ohm impedance matching correctly done. And the filtering also is a bit of a challenge. In the narrow band, the acoustics were predominantly and very successful filters. We'll see as we get into some quantitative numbers, they were very effective in the acoustic region. But as you go to broadband, you pretty much have to start using more RLC type circuits. So there are going to be new challenges coming because of that, and also the attenuation gets much worse as the frequency goes up, right? I mean, I think people are very familiar with this. Usually we're looking at 10 dB loss per kilometer, but if you start going to higher frequencies, you will lose almost orders of magnitude very quickly, right? So that's the EIRP budgeting is a big deal, and now to deal with this, you have to start outputting much more power out of your PA, and your LNA has to deal with a much lower signal, and you have to use complicated antenna strategies to boost the antenna gain as well. So all these things are major challenges. So these are not simple problems to be solved, and that's why things are not going to happen tomorrow. It'll probably take a decade or so to get all of this cleaned up and see which one actually works. Let's get into some technical details of these requirements, right? So let's start with the transmit side. We talked about the PA needs to output very high power, and the power added efficiency at the back off, right? So that you can't operate at the right of the edge, so because you need some margin, and when you back off, you should be able to have a pretty high PAE and a P out, and very good linearity. Linearity is what helps you to create good channel separations. Like if you want a certain signal to be in a certain band, it shouldn't cross over to the other, and how quickly it cuts off comes from their ability to get good linearity on your PA. And you're operating this at a very high voltage because you want the maximum output power, and then it heats up a lot of silicon, because in general the amplification efficiencies are not that good, and you generate a lot of heat. So the ruggedness of the device and the reliability tends to drive what kind of technology you pick, and that's a major problem in the PA as you start going into the terahertz bands. On the receive side, I think we already talked about, you need a high gain and a low noise floor, and there are lots of these harmonic generations, second harmonic and third harmonic, so you need very good intermodulation to manage that. And as the OFDMA gets more and more complex, you're trying to pack much more signals into the available bands, and your modulations, the quadrature amplitude modulations increase quite a bit. So we are now needing almost 1024 in many of the advanced applications. And the LNAs, of course, the thermal noise and the flicker noise are pretty big deal. Those are the biggest sources of noise amplification, low noise amplification. So, the flicker noise comes mainly because of the low frequencies. There is state changes, and the thermal noise is a channel issue. The gate oxide interface drives a lot of the flicker noise issues, and the channel quality drives a lot of the thermal noise. And in later generations of 5G, like sub-6 5G as well as the millimeter wave, we cannot use omnipolar antennas. The omnipolar antennas cannot deliver the power equally in all 360 degrees, right? But the power that you have is not sufficient with the attenuations at these high frequencies to be omnipolar and get enough signal for the LNA to pick up. So we do what's known as beamforming to solve this problem. And presently most of the production is all analog beamforming. You can think of beamforming as mainly a kind of a virtual wire that goes in air. The power is kind of directed significantly in the direction of where the receive is, as opposed to generally in all directions. And there's research going on to convert this to a digital beamforming in the next few years, so that will give you some advantage. And then you have the synthesizers where you need a pretty low power, and the DAC and ADC where it's all about the resolution. If you can go to 20 bits, they are pretty large and consume a high power, but then they give you a lot of resolution. And switch is about all the insertion loss, like the R on C off. you need a very low parasitics to as we switch the capacitance of the device plays a big role, and we'll see certain technologies end up being better than others for these reasons. The broadband filters that need to be at high Q and operate at high frequency and high bandwidth are again needed, and this is where I think you're going to see some very fancy advances in the acoustic to be able to go broader in their bandwidth, and then also combinations of the traditional RLC type filters getting in, and some kind of hybrid model where all these are coming together to solve the problem. So let's just talk a little bit about the filters, right? So in terms of the filters, there are a few key parameters that you look at. Like here on the table, I'm showing you the KT square and Q are two key parameters. KT square is a measure of how steep is the skirting, right? How quickly can you cut off the band you don't want? That measures the rejection KT squared. And the Q is how tall is the one that you want, how much higher can this be? And the delta is called the insertion loss, and a high Q filter usually gets this to be very high, right? So acoustics typically have very high Qs, and they are very narrow band. They are about 80 to 100. The RLC type filters, LC resonators, they have very broad band, but their Q is not as good, and their KT square is also not as good. They're kind of very broad of skirting, and they don't have a very high Q. So those are the challenges we have. How to get the coupling coefficient and the quality factor optimized for what you need to do depending on what kind of frequency you're at. There's lots of work going on in this area. Okay, so those are kind of the summary of all the needs of PA, LNA, transceiver, digital, and filters. So let's look at where the technologies are and what the challenges, more specifically, the industry is facing. Let's start with the digital. So digital, I think you probably heard this by now. It's no secret. Moore's law is slowing, and in the last few years, the transistors are not really providing fundamental single-threaded performance gains. The way people are able to solve most of their real-world problems is to go to multi-core, right? The transistors are shrinking at a fast rate. You can kind of put almost 2x the number of transistors like you had before in just 3 to 5 years, and therefore you're able to create more number of cores and do the workload optimization by splitting the cores and having them parallelly process as opposed to increase the frequency and running them through just one core. That's kind of what people have been doing. And in general, the technology cadence is slowing. Foundries are seeing much higher costs. So you're going to see, all these node changes are going to slow down a little bit. So it's a reality we have to deal with in adopting. But nevertheless, they do offer some improvement at 3 to 5 years. I think the industry is so hungry, they'll take it. So they are able to do well. All these foundries are doing extremely well because of that. And the power, right? We talked about performance slowing down, and here you look at power. The power, used to be when you went from a planar to a fin, you got some advantage in power, but then in a fin generation, it's very hard to get the power improvement. And the way fin generations get power improvement is simply depopulating the fin. As you go from 3 to 2, you got some 20% reduction in power, and you go from 2 to 1, you can get some, but then from 1, where do you go? Right? There's nothing left, and people are looking at gate all around and backside power as some really disruptive technologies to get this thing going. So clearly in terms of the engineering risk and complexity, people are doing really crazy stuff to get these power reductions and things happening, but the industry is so used to this cadence and process technology delivering power improvements that people are willing to pay a lot of money to get this. So I'll show you there are some crazy innovations that are going to come to help this. Let's go to the RF side. RF is far more complex than digital. I have to use kind of a quadrilateral to show you the various technologies and combinations. So we talked about in the double clicking the cell phone chips, what are in there. In the RF, we primarily had like a low noise amplifier, a switch, a digital side, and then a PA, right? So if you take these as four edges of a quadrilateral and look at what technologies are good for each, you'll find that, you take something like a PA, right? A 3,5 gallium arsenide is very good for PA. Most of the high-end phones use gallium arsenide PAs in your cell phones, but that's the only thing. There's nothing else you can do with it, right? That's kind of pretty. It's one of the very high mobility transistors that can put out a lot of power, and its ruggedness is very good. So it kind of serves that purpose. But if you look at the digital, the fin technology, later generation fins are extremely good at digital, but 3 nanometer is not good for practically anything else, right? It's kind of a one-trick pony as well. So if you want co-integrated for cost or insertion loss for other reasons, you got to look at other technologies. So in that regime, you'll see that PDSOI and FDSOI are pretty good. FDSOI ends up being one of our good technologies, which is kind of balances all of it. So in a millimeter wave front end where you want to integrate all of them in one chip, that becomes a reasonably good technology. Planar CMOS is also not too bad. It's very close. And then you also have PDSOI, which is much better for like a standalone switch. So it's very hard to beat a standalone switch performance of a PDSOI. So each thing has its own niche technologies, and how to get all of them put together in a system is the big challenge for the future. So let's look at a PA a little bit more. I think people are familiar with the Johnson limit, right? It's a P out challenge, and as you go to higher and higher frequencies, you lose 20 dB per decade in the output power that you can target. So this really kills your ability to put a lot of power at high frequencies. So your traditional semiconductor compounds are not very good. So there's lots of research going on in newer areas where the band gap is wider, like indium phosphide and gallium nitride, and if you need vertical transports, something like a silicon germanium HBT, and you can keep stacking the SOI. If you want many channels and kind of lower power, like in a millimeter wave base station that's very frequent, you can look at even stacked SOI. So all combinations are being looked at, and depending on what your application is and what kind of power you need. Okay, so those are some of the challenges. Let's talk about what are the innovations that are in the pipeline, right? So innovations have been the key, right? If I look at Qualcomm's modem and our cell phone in system integration, right, all the way from 1G, 2G, 3G, 4G, 5G, we've delivered a constant peak data rate increase, including, putting together the entire system, right? A modem plus digital plus transceiver plus the RF front end. The end result to the user, they see a product that keeps the same cadence. Our gigabits per second has been very, very consistent. And I think we'll kind of keep doing that because there are so many engineering options available in the toolkit. We just have to find out where we are going to get the maximum bang for the buck and go after that. So let's go to the digital. I mentioned before that we went from a planar here to the FinFET, and the fact that here the gate, right, this thing is a gate, was controlling the channel from only one side. And when you went to a fin, it started controlling the channel from 3 sides, and that helped you to lower the operating voltage, right? There's almost 150 millivolts reduction in operating voltage. So that's close to 20% right there, and that gave you a very significant power reduction. And I told you, as you go to one fin, there's no other option to reduce power. So you got to try to go get the gate on all the sides. That's called gate all around, or it's on all 4 sides. So that's going to give you certain more subthreshold slope improvement, and 20-30 millivolts you get to reduce the VDD. Not quite as big a VDD reduction like from here to here, but you'll probably get a third of that here. So you can continue to kind of do few things with this in the lower power. After this, it gets even crazier, right? People are talking about nano sheets, fork sheets, where NMOS and PMOS are built on the same sheet, and you're isolating them, and you can get some shrink based on this architecture. So, like I told you, these are really, really complex integrations and challenges for the foundries to do. But that's how crazy this is going to get, and people are putting in a lot of money and research to do this. And the bigger challenge is actually not just the front end. The fin and the gate all around and the silicon is actually generating pretty good juice, right? The cadence of how much juice the silicon generates is pretty good slope. The challenge has been the wires that are outside, they get narrower and narrower and suck up a lot of the juice and don't deliver it to the user. That's the bigger problem. So to solve that problem, we're going to split the way the interconnects are done into a backside and a front side. The backside will have fatter wires. The idea being fatter wires can bring in the current without a lot of IR droop and droop reduction, and you deliver a much higher voltage right into the silicon. And because the power is brought in through the other side, the front side is opened up for the signal lines. Now you no longer have to scale these front end lines into smaller and smaller pitches. You can retain them at a slightly bigger pitch and reduce the parasitics, and your capacitance is not as bad. And I think so this is a kind of a win-win combination that's going to get you a pretty good improvement. So these are all things that are going to come. People are clearly working on it. There is even definite roadmaps from companies when they are going to put these things into production. So there's still stuff out there, but it's going to be harder, and they are going to be fewer and longer time between them. So you can see a future where from 2022 to 2029, there are some things that are coming together that involves the gate all around, the backside power, and then you'll see some ideas on integrating them in different ways, putting the chips together in different ways, and creating 3D as kind of the future going forward. Okay, let's go into from digital to the radio frequency. So radio frequency on the transmit side, gallium nitride is the king of high power. Okay, so all the base stations pretty much eventually are going to be some form of gallium nitride. And I think these are very high critical fields, and they offer large drift velocities. So these are ideally suited. Indium phosphide is also a candidate because of its mobility. One of the best mobilities you have is indium phosphide, and the band gap is pretty large. So you will see that play a role as well. I think IMEC and others are doing a lot of research in this area. And then the CMOS and HBT will continue to play a role. I told you the future is where everything stays. Even though you're going to 6G, you'll still have stuff in 3G, 4G, and all of them are going to coexist, because all the base stations that have been installed and working, you don't want to give up on that bandwidth. And for immediacy and latency, those can play a big role. And as a part of the 5G, 3GPP standard, you got to find a way to guarantee certain things. And so all these resources need to be utilized. So all these older technologies are going to coexist, even though we're going to go to indium phosphide or gallium nitride 5-10 years from now. On the receive side, it's all optimized for noise floor, right? And the HEMT and PIMT are superior, but they are very hard to deal with. Particularly when you have super high frequencies, you cannot build a separate PA. You cannot take a gallium nitride PA, stick it next to a indium phosphide LNA, and that, because the connections and the insertion losses will play a huge role and deplete all your advantages. So there has to be a lot of co-integration thoughts and how to put all of this together. These are things that are going to play a big role. So I think the indium phosphides are pretty well researched on. I see a lot of activity in the industry in this area. So it's pretty, I think something is going to come out of gallium nitride, indium arsenide type of work that's going on right now. indium phosphide. Okay, filters, right? So we told you as a function of frequency and figure of merit, right? At the low frequencies, there is lots of options. The SAW and BAW are really acoustic filters, right? SAW is a surface acoustic wave, and BAW is like a bulk acoustic wave. And then there are various versions of it. There is the X bar, and then there is Qualcomm has its own Q bar, and so these kind of going to they're trying to increase the frequency at which these acoustic filters can work, and then that's pretty good. And then you'll see that the RLC like filters are pretty good at high frequencies, but like I said, their figure of merit is good, not good, because the KT square and Q are not that high, but they're doing some integration ideas to expand that. So this is the fertile ground for lots of research activity in the next few years to get to this place. Okay, let's talk about the 2D and 3D integration, where a lot of the RF integrations can happen. I think we talked a little bit about this while we are discussing the challenges. As you go to 5G, the matching has to be a part of your design itself. You cannot try to go after the fact and create matching circuits in the packaging or on the board to solve this problem, because now you're talking about really broad bands, and these transmission lines themselves are such large components of what's in the Smith chart that you cannot get away from designing for success right through these RDL layers in the package, or the transmission length in your chip, or how close your antenna is. All of them become a key part of how you engineer the Smith chart to get to the matching that you need, right? So the beauty is the technology to create these options is actually coming on board, right? So you can think of, like, I can go put this A on top of B if you can't afford a long line, or you can put A next to B, and you can create technologies, right? And then used to be we use only laminates, where there is a pretty low quality interconnect in the substrate, but now the OSATs have what are called RDLs. And these RDLs can be engineered to various thicknesses and quality of copper that you can control these things pretty well as well. And so all these things are going to have to be co-designed with the line length and the matching insertion loss, all of them into account, so that you can get one single solution together in the end. So that's really the holy grail of this. And I talked a little bit about the technology, so I want to help you understand what's out there, right? So you can think of these connection technologies, 2D, 2.5D, 3D, as controlled by the pitch of the density of connections, right? So if you take a really old, like a board, you can connect a board to a laminate package with a very low connection densities, hundreds of microns apart. You can very easily do that. This is part of production today. Everybody does this, right? This is so straightforward and so production technology. It's all clear. Now, as you go to 10 by 10 and 5 micron pitches, you get lots of options, right? So there is mold interposers, there is silicon interposers, and depending on what kind of routing and connection densities you need, you can go to, if you need a very high connection density, you can use a silicon interposer. If something like 10 micron is sufficient, you can use a mold interposer. This is cheaper, of course, and then you can do a number of vertical stackings, one on top of the other, and then more recently, you can also do die on die, like a vertical stacking, right? So there is technologies that are called chip on wafer and wafer on wafer that are pretty much in production these days, right? TSMC calls them like CoWoS and Info and all that, but there are others who do it too. So you can put these things together in many ways, and also you can put a wafer on wafer, right? So you can kind of bond the two wafers together, and CMOS image sensors use this in production today. So it's all kind of very near-term technologies that are available to make these integrations happen. And let's talk a little bit about the antenna. The classical antennas are the ones that are in a housing. And in the picture I showed you about Qualcomm's mmWave, I had a mmWave antenna that's kind of in a package, you can say, like it's a single laminate where I've integrated all the components and the PA and the LNA and also all the antennas together, patch antennas, how many ever number you want. Going forward, as you increase the frequency, the size of these antennas is going to come down, and these matchings need very high control and planning on how you're going to do it. So, from a package, they're going to get into the chip. I think that's the only way to get to a pretty robust antenna systems in the 6G and in those timeframes. Okay, so that brings me to how to make all these things happen, right? Today, if I look at how companies operate, the foundry and the IP kind of talk to each other, right? There's a technology that's called DTCO, and there is lots of tools and synopsis and cadence, and these guys provide mechanisms by which the standard cell can be optimized for a given process technology. PLLs and DACs and VCOs can be built with a very good understanding of the process, and there is a SPICE model plus simulation language that exists. But now, if you want to talk about antennas and you cannot build different RF components and in different silicon technologies and gallium arsenide and other things and put them all together, there needs to be a language where everybody can work together with, which is kind of missing right now, right? How to build a hard macro, how to build like a whole, not just an IP, but the whole system and optimize the entire process technology and package technology together. I think that's where the challenge is. And it really needs the industry to come together. I call this the system level co-optimization, STCO, and we need languages and toolkits and things to kind of bring all of this together. So that's really the challenge for the technology system, for the community. So in summary, I think I hopefully impressed upon you that we need a system level co-optimization, and we can look at the challenges for each of these systems. CMOS is really suffering from lack of Moore's law scaling. The power scaling is stopped, but there are some really breakthrough innovations that are out there which will come. There is enough appetite for and even though it's expensive, people are willing to pay the money for it. So I think they're just coming. In the transceivers, the first generation FIN is where we are right now. But going forward, we got to look at whether the gate all around may be good, but that's still a long ways off. In the RSTX, kind of the RF front end it's an alphabet soup of all the technologies. This is where 3.5s have somewhat of an advantage. So there's tons of research going on in various platforms. I think gallium nitride and indium phosphide are good candidates, but they're going to take 5 years or so to get to production. But PDSOI, FTSOI for switches and LNAs are going to stay, and silicon germanium for certain niche PA applications will be there. All of them are going to coexist. And in the filters, right, the acoustics is actually expanding, and they are trying to do a lot more bandwidth and push into higher frequencies. The thermal behavior is a big problem. I think the RLCs are also doing a lot of using 3D innovation ideas to get them integrated with the better form, and antenna and filters are going to combine together in an integrated system. So a lot of integration is the key, and engineers' ability to work across the board and collaborate is the real answer. With that, I would be happy to answer any questions you have. Thank you very much.
Hey, Chidi, thanks a lot for a fantastic talk and overview. Okay, so just remind folks, if you have any questions, please type them into the Q&A box. So we do have a couple questions pop up already. So one is on slide 14. What are the typical target specs of interest for the synthesizers, like performance, jitter performance numbers, and power consumption? I mean, I think this might be a little bit more too detailed for this talk, but
Yeah, I'm afraid I can't give you that type of detail in an open forum, right? Those are somewhat of proprietary type of numbers, but I think the from the metric and what matters, you're right? The jitter and those kind of details are the ones that we look for, and I can't give you very precise details of those.
that's understandable. Not
Yeah.
a big deal. Yeah, yeah. So if you have more questions, please don't hesitate to type. Certainly, I have a question here related to. Okay, so you covered a lot of different technologies here, and
Yeah.
this I believe is particularly more applicable to the handset or the user equipment where you really care about the low power and so forth. I was wondering, what about photonics? Integrated photonics. Does it have a role here, or you see this primarily just concentrated in the base station and in the edge and cloud, basically? Is this
Right.
something that even makes sense I mean, do we expect to see at some point the bandwidth's getting so high where it even makes sense to have an optical fiber or some optical data processing in the handset?
Right. So, it's an area where people have always looked at, right? I remember even 15, 20 years ago, people were looking for waveguides and transducers built on silicon to try to produce cost-effective, optimal, functional interface to the optical realm, right? But the reality has been these technologies have not reduce the interface, like to go from an electronic to optical transducer that's efficient enough and cost effective enough for it to get into a handheld kind of a space, right? They're doing very well as a fiber optic cable, even to get to the last mile. But if you look, they don't get very close to your home either. It kind of breaks apart in the cost structure to get to the final high volume units. So they're really there for low volume because their cost structure is a little bit higher still.
Yeah. Is it cost, or I mean, there's also like power and I mean, turning on a laser isn't exactly going to be easy.
Right,
Right?
right. That's true. Yeah. So that's true. In the L, the integrated system operation is the overhead, right? It's not easy to solve for very high volume user handset type of level, but people are able to solve it as once you get into a highway, then they're able to solve it because the engineering it takes and the customizations that you're doing are reasonable.
Yeah, makes a lot of sense. So another question came in for system level collaboration. You stated that engineers need to collaborate. That means tools and languages and standards. So this is a very practical question I also had. Is like, as companies are becoming more and more vertically integrated, what about the business barriers that like senior management of engineering companies put in place between companies, in terms of where these engineering teams reside?
Right. Yeah, no, I think within companies has always been easy, right? So that's never been a big problem. I think the bigger problem is like EDA vendors versus the foundry OSAT versus the design house, right? They can kind of think of them as three big groups. Is there enough interaction and collaboration to kind of break this and create a platform that goes across foundry OSAT to EDA to design house, right? That's one of the big challenges. I see a lot of momentum there. I see every company and every EDA vendor talking about it, and every foundry is able to do it, like big ones like TSMC and Samsung. That's where I see the problem is once you start talking about these 3.5s and OSATs and foundries, there are many players, and they are oftentimes reasonably small, like a gallium arsenide, right? Typically, gallium arsenide is built in WIN or AWC or a small foundry that is not quite capable of getting the entire system level thinking together. So what ends up happening is, companies like Qualcomm will drive a certain thing and take their stuff or create their own versions of it to solve the problem. So when there are small players in the semiconductor side of things is where I see some challenge, but we need to that's the one that we need to solve. But right now it's kind of being driven by the like Qualcomm's and other users are driving that kind of gap filling.
Got it. Couple other questions. So why is referring to slide 19? So from an RF performance perspective, why are FinFETs lagging?
Yeah. So if you look at a FinFET, maybe let me go to this graph, right? So here you see this is planar, right? And this is a fin. And the amount of capacitance that you have from a fin to fin is much higher than a capacitance you would have with a single gate sitting on a planar CMOS, right? So for a lot of the FMAX applications and as well as in LNAs and switches where you are looking for noise floors, and these parasitics play a big role. So fins in general are not suitable the way they are configured. But this is as an engineer, right? You can ask the question, why can't I build fins that are fairly separated apart? So I kind of reduce the parasitics, and then I can take advantage of the gate all-aroundness and the general GMGDS benefit that it provides. And we do ask that question, and it's complex for the foundry to go make something like that happen. Just for this, if they're going to go develop a whole process and the area goes up, do they see return on investment? It's not a clear answer. I can't say the answer is no. I think that's kind of where things will go. As people are finding, hey, my CMOS technology scaling is slowing down. I used to do one technology every year. Now I'm doing one technology every 3 years. What am I going to do with those engineers? You can go explore these kind of things. Can I take an older generation fin and move them apart and improve RF performance? You're going to see stuff like that happen pretty soon.
Yeah. That makes perfect sense. I was also going to mention, you mentioned gate cap is a big deal, but gate resistance is also a terrible thing with FinFET, right?
Absolutely, yeah, you're right.
Yeah.
Gate resistance is, and a fin is much worse because when you start doing high K metal gates, right, you stick so many things into that gate, and it's very hard to be conductive, and particularly the PMOSs are really terrible, right? So. There are again ideas on strapping with metals on top, and there's exactly those kind of innovations that are going to come in the future, targeted specifically at RF improvements.
Yep. I think I'm just, someone asked this question related to quantum computing. Obviously, there's no shortage of hype, if I may dare say, about quantum computing. Do you see it playing a role in communication systems at some point?
Yeah, the quantum computing is a change in paradigm, right? I think it's talked about, like Alvin said, hyped a lot. It's not a solution for all the compute problems, right? It's a solution waiting for a problem to be appropriate, because the way these qubits can work and solve are suited for certain types of problems, and not everything. And then also you need to get to really 0 Kelvin kind of to do anything real today. So I would say it's very early research at the moment, and they're going to be there and they're going to help the human civilizations, but we still haven't found the problem that they're going to be best to solve.
Yeah. I mean, certainly no shortage of attention being paid to it, but that's
right.
Okay, right? I mean, that's what this industry is. That's what drives this industry forward.
Absolutely.
What's that saying? If everything you try succeeds, you're not trying hard enough, right?
That's right.
Yeah. Okay. Well, hey, Chidi, I did want to, say thank you once again for this fantastic talk, and
Alvin, can you hear me, Alvin?
Yeah, sure.
Sorry, so I have one or two questions. Maybe we have time for one question if
Sure.
you guys don't mind send to host privately. The first question is about GaN and indium phosphide. Are there any commercial availabilities for operations on less than 10 volt range?
There is no commercial indium phosphide at all anywhere at the moment, right? I think the closest thing I can know is IMEC has done some research and they have created a startup right outside Belgium where they are doing some indium phosphide for labs. That's about the most commercial that's out there. But they do have visions of taking that into mainstream, and they are working with lots of people, but nothing yet.
Okay. And the second question, maybe we have time for this one only. So how to achieve a low cost price for 5G systems so that it can be widely used for IoT? This future semiconductor technology all looks very expensive.
Right. Yeah, if you look at cost curves for any technology, right, as the scale grows and as the user expands more and more and more, cost keeps coming down, right? So just by the sheer volume increase and time, cost comes down. And along the way, you will see customizations, right? So today, early 5G phones that are built to operate anywhere and everywhere, like I showed you, all the bands and all the features and everything put in one place, right? So it's kind of expensive. As 5G, particularly, in IoT space, where you're thinking about, putting a fridge or some doorbell in some area, collecting videos at high bandwidth for a long time, there it might be a custom, very small implementation where, once the volume for something like that exists, you can customize it, right? You don't have to make one solution to ship all over the world. You can make a solution where, okay, in San Diego at this home, you ship this. And if there is enough market for it and enough justification to go build a custom device, you can reduce the cost.
Yeah.
So, the market dynamics will kind of take us there.
Yeah, thanks.
Sounds good.
That's what I have, Alvin.
Jeff, I think we better close the meeting. Taking enough of Chidi's time. Hey, thanks again.
Hey, thank you. Yeah,
fantastic.
I really appreciate the invitation, and it was my pleasure. I really enjoyed it.